So today we're going to talk about a problem called the 4 cubes problem. Now, evidenced by its name, involves 4 cubes, and the objective is to take each of these cubes and stack them on top of one another such that we get a stack in which there are no two faces of the same color on one side. So here we have 2 yellow, I can't have that. I need green here or something. And then that messes up this side. So there's so many different options for each cube, which makes it tricky. But there's 2 ways of solving this. One is using prime factorization, in which we denote each of these as a separate prime and multiply them together to get a specific number because it would be unique. Or a different way is using graph theory, which is the approach I'm actually going to explain today. So first off, notice that each of these 4 cubes has 4 different colors. And notice that when we stack them, we're only concerned with the front and back and the left and right. We're not concerned with the top or bottom because those aren't seen at all. So when we get to our subgraphs, which I'll explain later, though we're going to arrange them in such a way that we have positions for the front and back of the stack and the left and right, which I'll get into. But first off, we will make graphs for each of these 4 individual cubes so that we know when we place blue, it's going to be opposite yellow. That's the vertices of our graphs are going to contain the colors of each face. So for instance, on our first cube, blue is going to be one vertice, yellow another vertice, and there will be an edge between them to represent the fact that blue is opposite yellow on the first cube. And we'll repeat that same pattern for all 4 of these. So on the first cube, like I said, blue is opposite yellow, red is opposite green, and red is opposite red, which is why our graph looks like that, with the edges between them representing opposite faces of the cube. And then the second cube is yellow opposite green, blue opposite red, and red opposite yellow. The third cube is red opposite blue, green opposite green, and yellow opposite blue. And finally, the last cube is green opposite yellow, green opposite red, and blue opposite yellow. So those are our 4 graphs. Now, in order to solve this problem, we want to be able to look at each of these graphs and see what edges they have in common and which edges that are unique to them, so that we can find a solution that's going to work for this 4 cubes problem. Because we can't have, well, I'll explain the stipulations later, I guess. But it would be kind of like the same thing as if we had 4 friends that wanted to get together to study. They can look at each of their schedules individually to see when the others have free time. But it would be a lot easier to see when each of them has free time to study if they took each of their individual schedules and placed them all in one schedule. So that's kind of what we're going to do here with graph theory. We're going to take each of these 4 individual graphs for each of these cubes and place them all in one big graph so that we can see what they all have in common and what they have distinct. That's basically what we're trying to do. So when we do that, we see here, this is what the graph looks like when we combine all 4 of these graphs for each of these cubes. And I will write that up on the board real quick. Notice that red is opposite itself in the first cube. Both cubes 2 and 3 are red opposite blue. 1 and 4 both have red opposite green. Cubes 2 and 4 are both green opposite yellow. And we have 3 cubes over here, 1, 3, and 4, in which blue is opposite yellow. We have 1, cube number 2, in which red is opposite yellow. And cube 3 over here is green opposite green. So here's here I've got drawn up on the board to kind of illustrate a few things about the stipulations for the two subgraphs. Remember earlier I talked about we're going to have two subgraphs that represent the front and back from left and right of the stack. Well, that's what we're doing here actually. So the first stipulation of each of our subgraphs is that each subgraph must contain one edge from each cube. So for instance, if we had something like this, if we took the second edge from here, first edge from here, and the fourth edge from here, this would be saying that, okay, for our first cube we'll have blue opposite yellow, second cube we'll have red opposite blue, but we don't have a place for the third cube, so we don't know how to position this. So this cube, since it's missing a 3, we don't even know where to place it, and therefore we can't have a solution because we don't have a position for the third cube. That's why I need to contain one edge from each cube. And for instance, then we can't just simply put another 4 here, like we have here, because then that's saying that for the fourth cube, we're going to place it in two different ways. We're going to place it in both green opposite yellow and red opposite green, which we can't place 4 in two different positions. We can only place each cube in one single position. Okay. So that's the first stipulation. And then the second stipulation is that each subgraph, the two subgraphs can have no edges in common. So that would be something like here, if we had something like this, and then we had so if my two subgraphs were like this, no. These are my two subgraphs. Now, this does not have an edge in common. This does not have an edge in common. This one, red and green, don't have an edge in common. Red and yellow, blue and green, they don't have any edges in common. But over here in blue and yellow, one is going to be positioned in both front and back as blue and yellow. So that'd be saying for my first cube, front and back is going to be positioned blue and yellow. And then for the left and right, it's going to be also positioned blue and yellow. Well, I can't, and the only way to do that is rotate the cube, which I can't do. Once I place it in one position, I've got to leave it there. So that's why the two cubes can have no edges in common, like you see here. And then lastly, the last stipulation is that we have a degree 2 for each vertice, meaning we have 2 lines coming from each vertice for each of our cubes. Now, the reason for why that is because, say for instance, if we had, green, or let's go with this one, yellow. So if we had two opposite, red opposite yellow on the second cube, then we had blue opposite yellow on the third cube, green opposite yellow on the fourth cube, and we have one over here. Okay? So we meet the first stipulation that the graph contains one edge from each cube, 1, 2, 3, 4. We, as far as we know anyway, we haven't done anything with the second graph to know if they have any edges in common. But we know by the third stipulation that I can't do this, because this would tell us that red is opposite green on the first cube. Then green is opposite yellow. Oh, no, red is opposite yellow. Yeah, red opposite yellow on the second one. Place it like that. Then blue is opposite yellow. Blue is opposite yellow. On the third one. And then the fourth one, green is opposite yellow. But notice that no matter what I do here, if I place green here, then I've got two yellows on the back. But if I place yellow here, then I got two yellows on the front. So when you have three edges coming from one vertice, you know that since we're only dealing with front and back, if it's the front of one and the back of the other, if there's a third one, it automatically has to repeat on one of the sides, either front and back or left and right. So that's why each vertice must be a degree 2. Which then leads to our conclusion, which you see here. Now, how we got there, I just wrote them up here. Notice that we can't have something like this where red is opposite itself. We have to get rid of that loop because we've got already blue going to it, and green going to it, and actually yellow going to it. So we have to eliminate this loop. Same with the green loop. We've already got red going to it, yellow going to it. We've got to eliminate that loop. In order to avoid this problem here with the yellow, because we've got red, as we explained in our one example, we can't have green going to yellow, blue, and red all going to yellow. So eliminate that. And then we just have to get unique pieces. So for the first one, this one's either going to be a 2 and 3, so that's easy that we can place 3 at one, 2 at the other. Then notice that this side can be 1, 3, or 4, which you don't know what it's going to be yet, so we're going to leave that. 2, since we already used 2 here, we know that 4 has to go here. And since we used 3 up here, we used 4 here, we've got to put 2 down here. We've got 1 and 4 over here. Well, if we, here, yeah, so for this one, we could have placed 1 and 4 on either side, and it wouldn't really matter, actually. Here, there are actually 2 solutions to this one. Not all cubes have, not all 4 cubes problems, depending on the arrangement of the cube itself, have only one single unique solution. There sometimes is a few. So yeah, then with that set, then that means that 1 is here if we've got 4 here, because we can't repeat, we can't have 2 edges in common between the 2 subgraphs. So then 1 would go here, 4 is here, and which leaves 3 there. Okay, so we'll notice that each of our graphs are labeled front and back, and left and right. Now it doesn't really matter which one's which. So we see for the first one, here we have blue opposite yellow, and red opposite green. So red opposite green, blue opposite yellow. Next one. Then we have green opposite yellow. Okay. Yellow opposite green. And red opposite blue. Red opposite blue. Okay. The third one is red opposite blue. blue, and blue opposite yellow. Okay, so blue opposite yellow. Okay, and the last one is red opposite green. Yes, okay. So red opposite green and green opposite yellow. So I'll place it like that. If I did this right, we notice that no color repeats itself no matter how we rotate the stack. There's the solution to the 4 cubes problem for this particular set of cubes. Thank you.